Alright, ladies and gentlemen, today we're going to learn or introduce work, energy, power, and potential. Alright, so I've opened up a document here, and as you can read here, it's written work, energy, and power. So it should include potential somewhere here. Okay, so we'll start with work. And here we're saying that if a force F acting on a particle gives it a displacement dr. Okay, so if the force F acting on a particle gives it a displacement dr, and you all know what displacement is. Okay, so this dr is just representing a change in displacement. Then the work done by the force on the particle is defined as dw equals F dot dr. As you can see, these are vectors, F dot dr. So what we're practically taking here is just the dot product of these two vectors. This is the force vector and this is the dr vector. Okay, so and in all cases you have to be given this force vector here. It has to be given in a question. Alright, and since only the component of F in the direction of the dr is effective in producing motion. Alright, so here we're just saying that the component of the force F in the direction of the dr is effective in producing the motion. Alright, so that's what we're talking about. And the total work done by a force F, or the force field vector, as you can see here in parentheses, it's written vector field. Okay, so F is the force in moving the particle from point P1 to point P2. So you see, looking at this diagram, we have a particle from point P1 here to another point P2 there. Okay, so this force F is the one used to move this particle from point P1 to point P2. This particle is moving along a curve, as you can see on this axis. So this is our X, Y, and Z axis in figure 3.1. Alright, so and here we're saying that the work done by this force F, in moving a particle from point P1 to point P2 is given by the integral of F dot dr running from P1 to P2. Like you can see here, it's written F dot dr from R1 to R2, which is just practically from initial position to final position. We're integrating from the initial position to the final position. So we're integrating that dot product of force and the dr vector there. And this same work done is also equal to the integral of F dot v dt running from initial time t1 to final time t2. So that's how we find the work done by a particle which is being influenced by a force F. And as you can see here, it's written where R1 and R2 are position vectors of P1 and P2 respectively. And here we're saying that V is just the velocity of the particle when time is t1 and time is t2. Here, this formula here, as you can see my pointer, this statement is talking about this formula here. So this is the other way of calculating the work done by pushing a particle from this point P1 to point P2. Alright, I'll repeat this statement. V is the velocity, this V here is the velocity of the particle, while t1 and t2 are the times when the particle is at p1 and p2 respectively. So t1 and t2 are just the times when the particle is here at point p1, and t2 is the time when the particle is at point p2. So that's just literally how we find the work done by a particle, which is a simple dot product and integration. And you can also calculate it by finding the closed integral of f dot dr. So this c here is representing the closed integral of a particle moving maybe on a closed curve. So this formula only applies when the particle has moved through a closed curve. That's why there is c, the closed integral of f dot dr. Alright, and then we have power. Of course, when we calculate the work, we also have to calculate the power here. So we're saying that power is just the rate of doing work on a particle. Okay, power is the rate of doing work on a particle, and the instantaneous power is given by P, as you can see here. This symbol P is equal to dw over dt. In other words, you can say the work over the time. So change in work over change in time. That's power. That's how we calculate power. And power can also be calculated by taking the dot product of the force and velocity, as you can see on this equation here, where my pointer is which my pointer is enclosing. This equation is saying that power is equal to f dot v, just the dot product of two vectors. So this is the force vector. In equation, you will be given this force vector, and this v will also be given. If it's not, you have to calculate it. If this force is not given in equation, then you also have to solve for it and find it. Then you take the dot product to find the power. Okay, that is the power used to do the same work. Alright, so we are introducing work, energy, power, and potential. In the next session, we'll look at some examples on how to solve for each of these subtopics. For each of these subtopics, we'll look at some questions which we can work with. Alright, so now we can move on to kinetic energy. Kinetic energy, as we all know, in first year we learned that kinetic energy is just the energy possessed by a moving object. Yes, that is the energy possessed by a moving object. Is called kinetic energy. So let's look at this first statement, which is saying, suppose that the above particle has constant mass, and that at times t1 and t2 it is located at p1 and p2 and moving with velocities v1 equals the r1 over dt and v2 equals the r2 over dt respectively. Then we can have the following theorem. Okay, so now we're looking at theorem 2.1, which is talking about work done being equal to the change in kinetic energy. So here this theorem is saying that the total work done in moving the particle along C. Okay, C is just representing the curve. Let's look at this curve again. You see this curve here in figure 3.1. This is the curve running from P1 to to P2. So this line, or this curved line here going all the way, that's our C. Alright, so I'll repeat this theorem. This theorem is saying that the total work done in moving the particle along C from P1 to P2 is given by work is equal to the closed integral of f dot dr, which is equal to half m v2 squared minus half m v1 squared. Okay, so this is just a change in kinetic energy. Here we're just saying that work done is also equal to the change in kinetic energy. So we can calculate the kinetic energy at point P1 and the kinetic energy of the particle at point P2. Taking the difference of those energies gives us the work done. As you can see, this is literally half mv2 squared minus half mv1 squared. Just the change in kinetic energy, we calculate the work done. Okay, and here we're saying that if we call the quantity T, if we say T equals half mv squared, we've called this T, the kinetic energy, as half mv squared here. The kinetic energy of the particle, then we're saying that theorem 2.1 is equivalent to the statement total work done from P1 to P2 along C is equal to kinetic energy at P2 minus the kinetic energy at P1. So that's what we're saying. Total work done is just simply equal to the kinetic energy at point P2 minus the kinetic energy of the particle at point P1. Or we can say in symbols, work equals T2 minus T1, where T2 here is just representing the kinetic energy at P2 minus T1, which is the kinetic energy at P1. Remember, these are just points on this curve which we've used as a reference curve for explanation. Okay, so that's it about work and the change in kinetic energy. We'll look at an example on all these notes which I'm just explaining here. We'll look at examples on each and every one of these notes. Alright, so now we can look at conservative force fields. Alright, conservative force fields. So this is another subtopic, conservative force fields. So here we're saying that suppose there exists a scalar function v such that f is equal to minus grad v, the negative gradient of v. So this symbol here is an operator called the del operator. This symbol here is called the del operator. Okay, so I'll read the statement again. Suppose there exists a scalar function v such that f, the force, is equal to the negative gradient of v. This operation here is called a gradient, the negative gradient of v. Okay, so this operation is called the negative gradient of v. Alright, then we're saying that then we can have the following theorems. So we'll go to theorem 2.2. Theorem 2.2 is saying that the work done in moving the particle along C, the curve from P1 to P2, is equal to work equals the integral from P1 to P2 of F dot dr, which is also equal to V at P1 minus V at P2. These V's here are representing potentials. So I was just saying that work done is equal to the potential at point 1, okay, the potential of the particle, or the potential energy of the particle at point P1 minus the potential energy of the particle at point P2. Okay, so you can even say here, this formula here, you can say force is equal to the negative gradient of the potential. Okay, so if there exists this scalar function V such that force is equal to the negative gradient of potential, then this force field is conservative. So this is what it means for a force field to be conservative. There should exist a function V such that force is equal to the minus gradient of the potential. So as long as this function exists, this V function exists, then this force field is conservative. That's what we're trying to say here. Alright, I know this this part of the gradient may be new to some of you, but I'll explain this in an example which we'll look at in the next session. But for this session, I'm just explaining the notes and what the statements in these notes mean. Okay, so this is what it means to be conservative, just this statement here. Alright, so one of the theorems we can have is this theorem 2.2, where we've said that the work done is equal to potential at P1 minus potential of the particle at P2. Alright, and we can say that in such cases the work done is independent of the path C. Okay, so the work done is independent of the path C for a conservative force field. So I'll repeat this statement. In such cases, the work done is independent of the path C joining points P1 and P2. So this statement is just saying that no matter what path we take, the work done will be the same. So the work done will be the same. It's independent of the path taken by this particle, as long as it is going from this point to the other point. So it's independent of the path. This is what it means for something to be conservative. If the work done by a force field in moving a particle from one point to another, so I'm just repeating this statement again. If the work done by a force field in moving a particle from one point to another is independent of the path. Okay, this is a very important statement. If it is independent of the path joining the points, then the force field is said to be conservative. Okay, the work doesn't change. You can take any path. Okay, so for example, you can go from Kitwe to Lusaka, maybe using a route which passes maybe instead of going straight from Kitwe to Lusaka, going straight by passing through Zambia, but then maybe you decide to go up in Congo, then go the other way in Angola, then Zimbabwe, then enter through Lusaka. You can still get the same work done. It is conservative. The work you do is the same. It's independent of the path taken. You get the same answer. That is what we're talking about for something to be conservative. Alright, and let's look at theorem 2.3 here. And theorem 2.3 is saying that a force field F is conservative if and only if there exists a continuously differentiable scalar field V such that F is equal to minus del of V. You can read this as minus del V, or if you want you can say minus grad V. It's the same. Or equivalently, if and only if del cross F is equal to kel F equals 0. So this is the other way of proving if something is conservative. So this is just one way of proving if a force field is conservative. So you may be given in a question a force F here. You may be given a force F, and this del operator, I'll show you what it is in an example. This is just an operator called the del operator. I'll show you in an example what it is. So you have to take this operation del cross F, which is you can read as kel of F must be equal to 0. The kel of F must be equal to 0. If you can prove this, then you have proved that the force field is conservative. If you can prove this, then you have proved that the force field is conservative. Okay, so this operation is a cross product, as you can see. We're taking the cross product of this del operator with a force F. So this force has to be given. This force has to be given. Alright. This is just another way of proving if a force field is conservative. You take this operation and you get 0, then you've proved your force fields to be conservative. Okay, so theorem 2.4, also talking about conservative force fields, and we're saying that a continuously differentiable force field F is conservative if and only if for any closed non-intersecting curve C. Okay, so if and only if for any closed non-intersecting curve C we get f dot r equals 0. So here we're just saying that the work done over a closed integral must be equal to 0. So this operation is just the work done here. So if this force field is taking a particle over a closed curve and you get the dot product with the dr vector, you get 0, then that force field is conservative. Okay, as you can see, this integral is different. It has got a circle here. This circle here is talking about a closed integral. This is a closed integral. This is how you represent a closed integral in mathematics. So the closed integral of f dot dr has to be 0 for a conservative force field. Alright, so that is I'm sure this statement already is just what I've just said here. That is, the total work done in moving the particle around any closed path is 0. This is a closed path. The total work done in moving a particle around any closed path is 0. Alright, so this is about conservative force fields. Now let's look at the last part where we look at potential. Alright, so now we're looking at potential energy here. Potential energy or potential. So we're saying that the scalar V. So remember this V. I explained V here. Yes, just on from the beginning of conservative force fields. I said suppose there exists a scalar function V. So this V is a potential. Suppose there exists a scalar function V such that F equals minus grad V. Okay. if this potential exists such that this condition is obeyed, then the force field is conservative. Alright, let's just go back to potential here. Alright, so we're saying that the scalar V such that F is equal to minus grad V is called the potential energy, or just the potential of the particle in the conservative force field. Okay, so the scalar V such that F is equal to minus gradient of V is called the potential energy, or just potential of the particle in the conservative force field F. Alright, we can therefore write equation A as work equals V1 minus V2. So work is equal to the potential at 1 minus the potential at point 2. Work is equal to the potential at point 1. Here this one is presenting potential at point 1 minus potential at point 2, or referring to the diagram we saw initially. Okay, I'll repeat this statement. Total work done from P1 to P2 along C. Total work done from P1 to P2 along C is equal to potential at P1 minus potential at P2, which is just that. So you may be asked to calculate the potential of a particle at different points. So if maybe the question is asking you to calculate the work done using potential, you just use this equation to find the work done. Alright, and we're saying here that we can express potential as V is equal to minus the integral of F dot dr from R0 to R. Okay, from R0 to R, or you can say from initial R to final R. We can say that that is how we can find the potential. That's how you find the potential. It is equal to the negative integral of F dot dr from R0 to R final. That is work done. Sorry, that is potential. That's how you find the potential using this formula. This is the formula used to calculate for the potential. Alright, so and here we are saying that where we suppose that V equals 0 when R equals R0. Okay. Alright, so we're saying here that potential is 0 for as long as R is equal to R0, because when we take the difference here after integrating, we have to take the difference and get the potential. But in this case, since we have supposed that if V is equal to 0, then we have to get rather if R equals R0, we have to get V equals 0. Alright, so in the next session let's talk about or rather let's look at some examples based on what we've just looked at, and these parts of the course. Alright, so see you in the next session shortly.